Day here on Taylor Polynomials. So we're just going to build off what we did last time, which is really just using this equation right here. But there is a little bit of a theorem where we'll talk about with error. So we're going to just touch on it now. We're going to hit it a lot harder later with Lagrange error bound. Pretty much saying that if a function is differentiable through this part of the Taylor polynomial, okay, if it's differentiable and it's containing c, it's interval. I'm just trying to say that this R value right here would be this guy right here, which is going to represent our error bound. So the remainder, essentially, that's what that is going to be our error bound. So we'll do that a lot more in depth later, but I really just want to focus on this first part. I know this is part of the theorem, but this is the formula that we did use on the first day to kind of rewrite. I'm going to ignore the R, the remainder portion of it. Everything underlined in blue, we should know. So given a second degree, that's what that P sub 2 means, second degree polynomial, and here, look, it even tells us that, Taylor polynomial about x equals 1. What are the signs of A, B, and C of the graph picture to the right? So here's our graph right here. So this is the graph of f. So don't forget, A is going to be f of 0. B is going to be, that's the one with the x on it, that's going to be f prime of 0, because we're sending it at 0, and c is going to represent f double prime of 0. Okay, because you can kind of see the formula right here. Yeah, one with x, one with x squared. That's right there. Okay, so what's f of 0? F of 0 is going to be some positive number. So this is going to be some number that is positive. So a is greater than 0. What's the derivative now? Well, this is increasing. So b is also greater than 0. And for the second derivative, this is concave up or down. Just look at it. Kind of looks like an N, so it's concave down. So c is less than 0. So that's all we were looking for that. Okay, so we're actually going to start to do Taylor polynomials going backwards, and that's what this was, our first step up, starting to go backwards now. So I'm going to give you the Taylor polynomial, some other stuff about it. Okay, so here we go. So we're given an approximated Taylor polynomial of degree 3 centered at 4. So you need to find the value of f4, f prime of 4, f double prime of 4, f triple prime of 4. So first off, this is right there is going to be f of 4. So f4 is going to be 2. Not a big deal. F prime of 4. That's going to be the x term. Is there an x term? There's not. There's a square term, but not an x term. So the coefficient would be a 0. So f prime of 4 is equal to 0. We're good. F double prime of 4, this would be the x squared term. Okay? And not only that, but don't forget, for the x squared term, it's going to be x squared term divided by 2 factorial. That's what it is. So what this is going to equal is right here. So this is going to be negative 5 x minus 4 squared, which equals, like we said, and let's go right here, the second derivative centered at 4 all over 2 factorial x minus 4 squared. Okay, so this is all for the second derivative. So the x minus 4 squared is x minus 4 squared. So the coefficient, this was negative 5, and this one's the second derivative divided by 2 factorial. So really, we got negative 5 is equal to the second derivative of 4 all over 2 factorial. So you just need to multiply both sides by 2 factorial. You're going to get f double prime of 4 to equal negative 5 times 2 factorial. 2 factorial is 2, so I'm going to get negative 10. All right, I'm going to start just boxing up what I got. And then I'll do the last part in green, that way, because I have a little room right here. Same thing's going to be true here for the f triple prime. So for f triple prime of 4, now that I kind of went through what this is going to look like, f triple prime of 4 all over 3 factorial is equal to this 8 value right here. Okay? So f triple prime of 4 is going to be equal to 8 times 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. So 6 times 8 is going to give me a 48. And those are my 4 terms for that one right there. So all we did was just work backwards. Part B, does f have a local maximum, local minimum, or neither at x equals 4? This is a fantastic question. So in order for f to have a local maximum, minimum, or neither, or even just any type of extrema, the derivative has to be 0 at 4. And, well, we do know that. So, boom, I'm good there. So now I need to figure out if it's increasing before or decreasing after, and I really can't. So I can't use the first derivative test, but I can always use the second derivative test. So look at the second derivative, and we said that that is going to be negative 10. So this, since it's concave down, right? So it's concave down, and let's say this is x equals 4, and we know that derivative is 0. This is going to tell us that we have a local max. So we have a local max at x equals 4 because f prime of 4 is equal to 0 and f double prime of 4 is negative. And that's the second derivative test. You don't need to write this down, but I will for your notes. Okay. All right, last example here. So the Taylor series about x equals 2 for a certain function converges to f of x for all x in the interval of convergence. The nth derivative of f at x equals 2 is given by, so it's just telling us what the nth derivative looks like. Write a third degree polynomial of for f about x equals 2. And remember that the nth term of the polynomial is this right here. Okay, so we need to find a lot of stuff here. We need to find our general, so we have our general term. Okay, so right here, this is going to be our general term. Okay, oh, this is going to be, used to find our general term right here. Okay, so if we were, I'm looking at this part right here. Okay, so if we were to take this right here, centered at 2, times this is going to give us our general term. So we're going to have this part right here, which is actually written right here, which is super nice. So f of n of 2 all over n factorial of x minus 2 squared. What is that going to look like? So I'm just going to literally just plug this in for right here. So this is my general term. So this is going to be n plus 1 factorial all over 3 to the n all over n factorial x minus 2 squared. Okay, so I'm just taking this right here, plugging it in right there, and I can simplify this just a little bit. So this n plus 1 factorial really is n plus 1 times n factorial. So I really can cancel out those n factorials here. So I'm going to get n plus 1 all over 3 to the n times x. This should be an n. I don't know why I put it squared. X minus 2 to the n. So this is my general term. Okay. So for a 3-degree polynomial of x is going to be this. So I had to find out what f of 2 is. So if I were to plug in a F2. Sorry, this is about, okay, I'm just rereading the problem here, making sure that I am not missing anything that I need to tell you. Yeah. So for this third degree polynomial, f of 2, that's what I was looking for. I was like, where do we know that? Okay, so f of 2 is 1. That's great. So I get 1 plus first derivative. So plug in a 1 right here, and I'll give us our first derivative value. So we're going to get 1 plus 1. Sorry, it's right here. This is a simplified version. So it's going to be still 1 plus 1 over 3 to the 1 times x minus 2 to the 1 plus 2 plus 1, 3 squared times x minus 2 squared plus 3 plus 1 over 3 to the third x minus 2 to the third. There we go. So it's really helpful to give us that first term, otherwise we would have been stuck. And now let's go ahead and simplify this. We're going to get 1 plus, it's going to give me 2/3 x minus 2 plus, this is going to give me 3 over 9, which is just 1/3, plus 1/3 x minus 2 squared. Plus, this is going to give me 4 over 27 x minus 2 to the third. And that is my simplified answer of my third degree polynomial with our given information here. So essentially, we went backwards to figure out our Taylor polynomials based on our information that was given. So sometimes it just gives us the polynomial itself to figure everything out. Other times it gives us just the general, not the general term, but it gives us parts of the general term. So we can find the general term, and then I used this guy right here to plug in here, there, and there. And I couldn't use it to plug this in because that's my constant term, and this doesn't tell me anything about my constant term. This only talks about my derivative term. Okay, and that's going to wrap everything up on day 2 for Taylor polynomials.